All right, so it's time for the main event. Today's speaker, of course, is going to be Kwasi Wrensford. Kwasi, of course, needs no introduction, but he's going to get one from Ireland.
Been waiting a long time. All right, so yeah, it's my great pleasure today to introduce Dr. Kwasi Wrensford, who completed his degree in August, and he's not advancing this one. Okay. Interesting. There we go. All right. Completed his degree in August. So Kwasi came to Berkeley in the fall of 2017 after completing his undergrad degree at UConn, where I think he took every class in ecology, evolution, and vertebrate biology that they offered. Okay. But while he was an undergrad, Kwasi also worked with Dan Blumstein as part of the long-term, 60 plus years now, long-term study of yellow-bellied marmots at the Rocky Mountain Biological Lab. I think Dan's on the call here today, so he can vouch for that. But this turned into Kwasi's honor thesis, which is now published and which examined the spatial geometry of anti-predator responses in the marmots. So when Kwasi applied to Berkeley, interested in field studies of mammalian and in particularly sciurid behavior, how could I say no, right? I'm very happy that he chose to do his degree here and to spend the last few years working with me in my lab. So we all know Kwasi, right? And I think the size of the crowd here today and online reflects how central a member of our community he's become during his graduate career. I'll see if this will advance. Among the things Kwasi is known for are his love of natural history, his mac and cheese creations, and just his generally always positive, engaging personality. So while it's true that Kwasi has been a huge part of the social fabric of the MVZ and IB, he also has a deep love for open spaces. So whether he's enjoying them in a group, this was in Alaska this past summer, right after the Mammalogical Congress, or alone, there's very much a theme in photos of Kwasi, right? Outdoor spaces, lots of natural beauty, things like that. Well, I want to be sure and acknowledge Kwasi's professional accomplishments. Here he is, full regalia last May at our commencement ceremony. He is now Dr. Wrensford, and that's not a trivial undertaking or trivial achievement, right? I knew somebody would get to the sound makers early, right? Yeah. But I confess, when I think of Kwasi, I think of this person, okay? That's the image I have in my head, the outdoorsy, nature-loving person who always has this positive perspective on things. And in part, I think that's because Kwasi really knows who he is and what excites him. And I was first struck by this when Kwasi visited campus during his recruitment weekend, that back pre-pandemic, we used to all get together, usually Saturday night at Jim's house, for a pizza dinner with all of the potential recruit students. And, I can remember that usually the potential new students, quite understandably, were kind of quietly standing there looking a little concerned, being in this crowd of many loud, boisterous vertebrate biologists all expounding about their favorite animal. In contrast, I don't know if you remember this, Kwasi was totally at home, and I have this really vivid memory of Kwasi in Jim's kitchen with beer in hand, totally holding court, holding his own with the rest of us. He was dressed like this. In fact, it may have been the same outfit. So just visually superimpose Jim's kitchen with the table here, the patio there. And that was Kwasi from the get-go. He was completely at home, totally holding his ground with the rest of the vertebrate biologists in the museum. And I remember thinking to myself in that moment, this person belongs here. And I think that's absolutely proven true, both from an academic perspective and from the perspective of having a great colleague who has spent the last several years with us. That said, there have been a few moments along the way. This photo is from the first day of Black Birders Week. I don't remember which year, but clearly pandemic. And I saw this kind of like, Kwasi? And then I found this photo where he's clearly questioning for himself the taxonomic assignment of that animal in his Black Birders Week, okay. I think fortunately now we do have evidence, though, that Kwasi has learned to discriminate birds, modern birds, And so I'm confident that now that he has graduated and moving on, he understands that difference. But more seriously, sorry, you knew I had to take this. More seriously, Kwasi has been an amazing role model. A role model for how to love nature and how to share that love with others. So in addition to his accomplishments as a scholar and a researcher, he's been an exceptional ambassador for natural history, particularly with our undergraduate students. And again, when I think of Kwasi, I think of photos like this, where he's surrounded by students, sharing with them some animal usually that he's just picked up or just spotted, or sharing some of that love of natural history. I've learned a lot from Kwasi, both from our academic discussions and from watching him in action with others. So this is always the bittersweet moment, right? Well, I'm thrilled to see Kwasi finishing his doctoral degree and moving on to the next phase of his career at UBC. I'm really going to miss him here in Berkeley, and I think I'm not alone in that sentiment. So with that, I'll turn the floor over to Dr. Wrensford.
Thank you for that introduction, Eileen. That was really sweet and embarrassing. Yeah, so thank you everyone so much who's here in person and everyone who's on Zoom. Yeah, it's a very bittersweet moment to be in front of the seminar that I've gone to every Wednesday for the past 6 years of my life, presenting what I've been working on for the past 6 years of my life. I'm looking forward to kind of sharing with you what the chipmunks have been up to over in the Sierras. Hopefully you have fun, learn a little bit, and we can both kind of appreciate these beautiful animals that have captured my attention for all this time. So here at Berkeley, we don't have to do formal dissertation defenses. Those of you with PhDs are probably just kind of grumbling to yourselves. They have it too easy over here, you know. But we still have the tradition of the finishing talk, which I think is nice, because instead of this being like a trial or a test, it's more of a celebration of the work that you've done. And it reminds me of an album by the late great rapper Nipsey Hussle. So we're gonna call this my victory lap. And so before we get started, I just wanted to lead with the acknowledgements. And there's so many people that I probably could not fit on the slide, and I probably should have. But if you're not on the slide and you helped me in any way, you were indispensable to getting this project done and making all of this happen. Especially want to thank all the members of the Lacey Lab, past and present. You guys have been my rock here, and I couldn't ask for a better community. To my undergraduate volunteers who helped with my museum and field and lab work, to my dissertation and committee, Daniel and Wayne, Michael, who's off lounging in Spain right now, and George Bentley, and then to so many more, particularly all the staff and community members in the museum, Chris, Terry, Lomania, Carly, Carol, Lydia, Jim, Fred, Carl, and everybody. I really, really appreciate you. Of course, all the people who've given me money that I've but a field biology project would not be complete without acknowledging the people who actually were out there with me collecting the data. So to these 11 people who came out with me the past 6 years, I appreciate them so much. This is their project as much as it is mine. And I know some of them are on the Zoom and are able to see, and I'm so happy they can see all of their hard work laid out in the final story. So to the science. So today we're gonna be telling a story in kind of 4 parts. First, kind of take you through some of the natural history and background of the chipmunks and their environment. Then getting into a discussion of population, demography, and ecology. And then getting into differences in behavior. And then kind of a follow-up to my studies of behavior, looking at repeatability and personality. So first, our background in natural history. High elevation ecosystems, the mountains, they're beautiful, right? But they're a difficult place to live. It's cold, not a lot of oxygen, really dramatic swings in weather and climate. But in spite of all this, a bunch of species call the mountains home and have developed unique and robust adaptations to live in these environments. However, as the climate changes, as the planet warms, these high elevation species are at unique risk and unique threat under climate change. As these temperatures warm, the growing seasons change in their duration, winter snowpack gets thinner. And so studying mountain ecosystems in particular can give us a really good lens into how climate change is going to affect species the world over. In response to changing climate, species across the globe often shifted their ranges and poleward or higher in elevation in response. Despite of the prevalence of these range shifts, we see a lot of variation and heterogeneity in the prevalence, the incidence, or magnitude of these range shifts. This figure here is kind of busy, but you can kind of tell yellows mean expansions, reds means contractions across an elevation of transected mammals in California. You can see that there's just as many yellows as there are reds. So there's just as many species gaining ranges as there are losing ranges. And so understanding these range shifts and what drives them is a really key question as we move forward in understanding the effects of climate change on wildlife and animals. And so a lot of this work, our understanding of range shifts, particularly in California, comes from work done right here in the Museum of Vertebrate Zoology. So 100 years ago, our esteemed first director, Joseph Cornell, led a series of surveys of California vertebrate fauna species across the state of California and the mountains and the deserts and the coasts, and took meticulous field notes and instructions for how he conducted those surveys. These were indispensable for future researchers 100 years ago to come back, take those notes, and redo those surveys with the exact same methods and localities and effort. And then therefore, they can then compare with those surveys done 100 years ago and see how species presence on the landscape has changed over the past 100 years. As that figure I showed you earlier indicated, those changes are really varied across different species. And we even see really big differences in closely related species as well. Which brings us to the stars of today's story, the lodgepole chipmunk and the alpine chipmunk. Also, real quick, I need to shout out one of my field techs, Snell. Most of the pictures, wildlife pictures, the good ones anyway, you see in this presentation are hers. So got to shout her out as well. But anyway, so these are the two chipmunks, the lodgepole and the alpine. So both of these species are kind of in the central Sierra Nevadas, kind of around the Yosemite area. These are the species you'll find at the highest elevation levels you'll find chipmunks. They both live in these higher elevation habitats and often co-occur and share habitat, but they have remarkably different responses to the past century of climate change. So historically, Tamia speciosus, the lodgepole chipmunk, in the central Sierras has occupied this elevational range, while the alpine has occupied kind of this elevational range. And so while they kind of occupy similar elevational or different elevational zones or distinct zones, there's this really broad region of overlap right here, kind of surrounding 9,000 and 10,000 feet. However, over the past 100 years, the resurveys have revealed a really steep contraction of alpinus's elevational range, while in the same region, you don't see the same kind of contraction in the lodgepole chipmunk. So that region of overlap is narrower. The alpine chipmunk is moving further upslope in response to that changing climate. And so what's different about these two chipmunks that live in such similar habitats that might explain such disparate responses to climate? And so, first of all, these chipmunks prefer very different microhabitats. So even though they co-occur in similar environments, in fact, when I do my trapping, I can collect both species in the same traps, like one next to the other. In the landscape and in their day-to-day lives, they're using very different habitats. So lodgepole chipmunks prefers much kind of denser forested cover, kind of at mid elevations, and then the alpine chipmunk prefers more open and rocky environments, kind of at the higher elevation limits that you'll find chipmunks. This is work based off of Rachel Walsh's dissertation, another former Lacey Lab chipmunk expert. These chipmunks also have differences in their dietary niches, where we see through stable isotope data that alpine chipmunks have a distinct and narrower isotopic ecological niche than the lodgepole chipmunk. Basically, through these stable isotopes, we can tell what ratio of different types of food that they're eating, ratio of plant material to animal material, or different types of plants. And then also with the alpine chipmunk, we see selection on the shape of its skull that we don't see in the lodgepole chipmunk, another clue that they might be specializing their diets in a way that we're not seeing in the lodgepole chipmunks. these alpine chipmunks are specializing to their high elevation life in their genetic traits as well. And work also done in the museum has shown that there's been rapid selection on genes underlying response to hypoxia in the alpine chipmunk that we're not seeing in the lodgepole. So all this evidence together tells us that the lodgepole chipmunk here has a more generalist ecology, while the alpine chipmunk has a more specialist ecology. The commonly observed pattern we see in generalists and specialists is that generalists, tend to have much larger geographic ranges, and they also tend to be more resilient to changes in the environment, and less likely to go extinct under climate change, while specialists more likely to go extinct under climate change and tend to have smaller geographic ranges. So that sets up a really interesting comparison between these two very similar species, in that we have this generalist and we have this specialist, and they both seem to be doubling down on their strategies of generalism and specialization to deal with the changing climate. So how's that working out for them? So our next section, we're going to talk a little bit about some population demography and ecology. And so what demographic processes are associated with range shifts? So species range shifts are often the emergent result of underlying population dynamics. As populations grow, individuals disperse to find open habitat, pushing range boundaries across the landscape, right? Underlying demographic vital rates, things like growth and body condition, the ability of individuals to acquire resources, reproduction, to successfully rear offspring, and survival, being able to avoid all the things trying to kill you so you can keep doing those other two things. Those are all really important underlying mechanisms that drive population growth rates, and in turn can drive those geographic patterns that we're observing in the landscape. So understanding those mechanisms and how they're affecting populations is key to understanding the mechanisms driving the range shifts we're seeing in response to climate change. And so scientists so far have been starting to tease out how these different vital rates are being affected by climate change. And as in all things in biology and ecology, the answer is it's complicated. But we kind of are starting to see a few emergent patterns here, is that warming temperatures tend to lead to longer growing seasons and positive effects on vital rates. So in a lot of species, particularly this review here by Wells et al. Was done in hibernating small mammals, warming temperatures tends to lead to higher growth, higher reproductive output. However, climate change isn't just all about warming temperatures, right? So along with changes in temperatures, also changes in the precipitation regime as well. And what you start to see is that while warmth might tend to have positive effects on vital rates, decreased temperature that often comes with, or decreased precipitation that often comes with those increased temperatures tend to have negative effects on vital rates, which is particularly critical for hibernating small mammals. The winter precipitation in the form of snowfall, that snowpack layer is really important for helping individuals stay insulated and help them survive through the winters and hibernate. And so all of this evidence together and the available data seems to indicate that although there's these kind of competing effects, that hibernating small mammals are projected to be negatively affected overall by climate change, although again, it is complicated. Our chipmunks, for example, we start to see some evidence that there's effects on their population dynamics as well as effects on the other traits that we discussed earlier. And particularly in Thames alpinus, the alpine chipmunk, we see an erosion in genetic diversity over time. So species are becoming less genetically diverse over time and more isolated over time, which is indicative of populations that are not growing, but shrinking and becoming, and there's less movement and dispersal between populations. Along with the physiological adaptations alpinus has for high elevation life, evidence points to declining populations in alpinus and stable populations in speciosus. However, we do not actually have year-to-year demographic information on these chipmunks. So that leads us to these important questions then. Are differences in demography associated with patterns of range shift in lodgepoles and alpine chipmunks? Does the lodgepole chipmunk have better body condition than the alpine chipmunk? Do they have higher rates of reproduction, and do they have higher rates of survival, which would be indicative of a population that's surviving, thriving, and growing versus a population that's shrinking? So we conducted this fieldwork in eastern Sierra Nevada mountains of California, around Yosemite National Park in the National Forest land in that area. So we worked at 3 different sites over the course of this fieldwork: 20 Lakes Basin and Saddlebag Lake, which are on opposite ends of the Saddlebag Reservoir, which is right off of Tioga Pass, if you've ever driven through Tuolumne Meadows. Highly recommend if you're trying to look for a place to hang out in the Sierras that's not as crowded and crazy as Yosemite. It's just as pretty, and there's like a tenth of the people. So here's your fun tip. And so these sites are both sites where lodgepoles and alpines co-occur. I've caught both of there pretty consistently and various numbers, which you will see. And this site's about at 9,000 to 11,000 feet where I do my trapping. And it's kind of a mix of open white bark forest and some alpine meadows. And then the third site here is a bit further south, closer to the town of Mammoth Lakes. You might know that as like hot ski town there. But there's a lot of really good natural space there. It's right off of the John Muir Trail and lots of fun things. And so this site is a site where only lodgepoles are found. Alpines were found there historically, but since then, it seems like they're no longer around after many years of trying to find them. But this site's a little bit lower elevation, a little more forested, kind of more of that typical closed overstory lodgepole habitat that they like. And so our trapping methodology would set live traps to collect these animals, and we sampled these sites from 2019 and 2022. And then once we've captured an animal, we mark them with a metal ear tag, or starting in 2020, an RFID pit tag, so we can uniquely identify each individual going forward from year to year. And then each individual was weighed, measured, and sampled for tissue pieces. And so here's kind of a summary of the trapping that we did. So over the course of the study, we've caught about 220 lodgepole chipmunks, speciosus, and 71 alpinus over the course of that study. So as you can see, really big disparity in the densities and the capture success of those in the areas where they overlap. And anecdotally, I can tell you those numbers are getting lower and lower every time I go. Yeah, kind of a bummer. And that's reflected in the numbers too across years, that the lodgepole, the speciosus, tend to have higher population densities across all sites than the lodgepole chipmunks. And however, over the 3 years, or over the 3 years of the study where we have consistent year-to-year individual ID data, we don't see much of a difference in population densities across sites, except in this one site where we had this massive spike, or this massive change in density. And that's because at that one site at Arrowhead Lake in 2020, there was a massive baby boom, like crazy. We were catching like 50 babies a day. Like, it was wild. But as baby rodents are like to do, like, they don't usually last that long out there, especially when they're that dense. And so the population, of course, kind of attenuates back to a more stable level over time. And so this kind of gives us a sense that, again, we sort of see these sort of species differences in density, but we don't see a lot of variation from year to year, except from that kind of one spike. And that's kind of a common pattern you see in sort of rodents, right? You kind of see these periods of low stable densities with these really dramatic spikes in populations and really quick attenuations back to the baseline. So one of the things that we measured while we were capturing our chipmunks, we measured body size to look at that body growth and body condition question. And so this data is pretty simple. It's just a regression of body mass and body length. And so that kind of gives you a very rough estimate of the species of an individual's fitness, right? So how much of its body composition is kind of extra weight in terms of fat, which translates to more energy available to do things, right? And so what we see is that lodgepoles are bigger than alpines. We knew that already. But what we're really interested in is looking at that body mass, the relationship between body mass and body size, right? So that we know they're in general bigger, but one species kind of better at sort of gathering resources, retaining weight, and building that body fat and extra energy reserves. And what we see is that we see kind of a steeper relationship between body mass and body length in the lodgepole chipmunk than we do the alpine, which might kind of tend to lead us to think that they tend to have better body condition. However, a statistical test in ANOVA revealed that relationship was not particularly significant. As you can see, there's a lot of scatter around the trend line, and there was a lot of variation. But when we collected for things like sex and excluded juveniles, this pattern didn't really change much. And so we also wanted to get another questions of body condition using a sort of a more refined measure of body condition. So we use something called the scaled mass index. And so it's basically a way of normalizing for body condition across body size and body mass using a regression, a standardized main axis regression method. So this is, I promise, is the only equation you have to see this whole presentation. But basically, it just gives us another tool at which to compare body condition within species across different contexts. So the scaled mass index is species specific, so we can't compare scaled mass index directly between lodgepoles and the alpines, but we could compare them across sites and across years and see if there are patterns in those contexts that hold true for both species. And what we tend to see is that at one of our sites, Arrowhead, lodgepole chipmunks tend to have better body condition overall than at the other two sites, which tends to make sense with what we know of this site in terms of those higher numbers. It's kind of lower elevation, it's wetter, the winters aren't as harsh, so it kind of makes sense that individuals from there tend to have better body condition. And then another pattern that we see is that in both species, body condition jumps up a lot in the year 2022 across all sites. And I don't know why yet. One of my hunches is that winter was a pretty heavy snow year. And so we're thinking that led to a bigger flush of primary productivity and more available forage. And so that was why we see that difference in body condition. But yeah, so that's body condition. Next, we kind of get into issues of reproductive output and sex ratio. And so this is just a kind of a brief look at the sex ratio between our two species. It's kind of more of a descriptive character, but kind of gives you a sense of what the reproductive landscape is for these individuals. And as you can imagine, a more female biased sex ratio might lead to a better reproductive output than a more male biased sex ratio, right? And so we don't really see a difference between species. We do see a little bit of differences between year and locality, in that there seems to be, again, a real jump in the male bias in 2022, particularly in the alpines. But again, it's a pretty small difference, and it doesn't seem to make a big change into the overall patterns we see. Along with the field data that we collected for reproductive output, a student of mine, Yian, went into the museum specimens to look at specimen tags, to look at whether or not individuals collected across the sites that we studied historically have placental scars. Basically, when a individual is pregnant and they have their babies, the babies leave a little scar on the uterine lining. And so that can be a good sort of proxy for determining how many offspring an individual had in a given season. And so we went into the museum specimens, looked through both alpine and lodgepole chipmunks. Shout out Jim Patton for those specimen collections. And we found that while there was a little bit of variation in mean litter size between the two species, it was not a statistically significant difference. That's a hard thing to say. And then we also looked at sort of the proportion of individuals in that sample who had evidence of any reproductive scarring. So they were reproductive that season, or they were not reproductive. And you also didn't see any real difference between the two species. Also, as well, when we get to age structure, the proportion of juveniles that are collected in a given season, we don't see much of a difference between species, except again, in 2020, there's this huge baby boom in Arrowhead Lake. But overall, the pattern across all the other years remains the same. So that's reproduction, and we don't really seem to see much of variation. So how about survival? How about the likelihood that you're going to make it from one year to the next as a chipmunk? So recapture rates tended to be pretty low overall. So across the portion of years that we have consistent individual IDs, we only tend to see about a 9% recapture rate. So of the species individuals that we capture, only 9% of those will recapture the next year. And that can be due to a variety of reasons. Again, this is a very coarse measure of survival. So that could be due to mortality, it can be due to dispersal, it could be due to imperfect detection, it can be all sorts of things. But it gives us a place to start to sort of estimating what the survival might look like between these two species. Recapture rates did tend to vary across years. For example, during the 2021 field season, the overall recapture rate was about 10%, while in the 2022 field season, it was about 28%. So there was a pretty big spike in recapture rates. And in general, lodgepoles tended to be more likely to be recaptured than alpine chipmunks, where in overall, lodgepole chipmunks had about a 32% recapture rate, while alpines had about like a 9% recapture rate. However, differences weren't particularly statistically significant, again, because of since recapture rates were so low, sample sizes were low, it's hard to come up with a very definitive pattern about the differences in recapture rate. So, going back to our questions, are differences in demography associated with patterns of range shift in alpines and chipmunks? Does the lodgepole have better body condition than the alpine chipmunk? Yeah, kind of. And so does the lodgepole have higher rates of reproduction than alpine? Definitively, we can pretty much say that no, there's not really a difference between species. There's differences in other contexts, but those don't seem to be related to species. And then does the lodgepole have higher rates of survival than the alpine? Yeah, maybe. And so some of the take-home points then is that body condition varies significantly by locality and year, but not by species. The lodgepoles tend to have higher recapture rates, implying higher survival, but this difference isn't particularly significant. And then these population variation that we are observing that's driving these range shifts might be more due to extrinsic environmental factors rather than intrinsic demographic variation. So rather than kind of the intrinsic machinery of population variation, birth, death, birth mortality, and dispersal, these kind of more external environmental conditions in terms of changes in the available landscape and the habitat, and like big stochastic events, things like weird precipitation years or avalanches can have really big effects. And we have evidence in particularly in other short-lived, highly fecund species, that these stochastic events have really strong effects on population dynamics over time. So that's the ecology. So now we're moving on to the behavior. So in this chapter, I focused on two particular behaviors that might underlie how species deal with change in stressful situations, and how that might in turn help them survive a changing climate. So how might species persist in altered habitats? Behavior is the most immediate mechanism that for animals to respond to environmental change. And organisms with broader behavioral toolkits, more strategies at their disposal, may be better situated to respond to climate change. And so two of the behaviors that I chose to focus on with the chipmunks are behaviors called boldness and exploration. So boldness is described as an individual's willingness to engage in risky behavior or risky or unfamiliar behavior. And then exploration is individual's willingness to interact with a novel or unfamiliar environment. And so these two behaviors are prevalent and measured across a variety of taxa, whether it be fish all the way to birds. And these behaviors can also co-occur and co-vary in similar contexts, forming a behavior, what we call a behavioral syndrome. I'll talk more about those later. And so in particular, these two behaviors have gotten a lot of attention in understanding how species and how individuals are coping with a rapidly changing environment. For example, dark-eyed juncos that are colonizing novel habitats tend to be more exploratory and are less physiologically stressed than birds from their ancestral habitat. Urban coyotes are bolder and more exploratory than rural coyotes, with individuals varying across a wide spectrum of behavioral types. And in eastern chipmunks, Tamia striatus, individuals with either high or low levels of exploration show increased survival compared to intermediate explorers. And so we see that there's a lot of variation in kind of how these behaviors present in populations, but there seems to be mounting evidence that these behaviors might offer species a tool to cope with an unfamiliar or rapidly changing environment. In our chipmunks in particular, we're starting to see evidence that their responses to stress and the unfamiliar is really important to how they're dealing with their environment. And so work done by another previous Lacey Lab student, Tally Hammond, looked at their physiological stress profiles and how those differ between the species. And in this validation study, she did a simple validation challenge where you take an animal into captivity, inject it with ACTH, which is a hormone that stimulates the release of glucocorticoid hormones, which are a common stress response hormone, and then see how their stress profiles or their hormonal profiles change over time. And what you can see is that, so this is the onset of the test. And so the dotted line is the hormone challenge, and the solid line is the saline control. And you can see at this onset here, which is about 12 hours or 24 hours later, you can see in the alpines this huge spike, both in the control and in the hormone profile. While in the lodgepole, you see a spike in the hormone profile, which makes sense. They're being artificially injected with this hormone that stimulates a physiological stress response. But in the handling control, nothing, flat. And so you can see that these lodgepole chipmunks, when it comes to being acutely stressed out, don't have the same elevated responses as the alpine chipmunks. We sort of see a similar pattern on a more environmental scale. When we collect fecal samples from these animals in the wild, we can measure for hormonal metabolites that kind of give us a sense of what their sort of baseline circulating levels of stress hormone are. Now we can see that in areas of higher, or in sites where the maximum daily temperature is higher, we see elevated levels of stress hormones in the alpine chipmunk, while in the lodgepole chipmunk speciosus, it remains flat. And so that gives us pretty good indication then that these species are responding to stress and responding to the unfamiliar in very different ways on a physiological level. And so that raises an important question then, does that translate into their behavior? So we see increase in boldness and exploration to cope with these changing environments and keep those stress levels managed. And can they mitigate those responses to climate change? And so that leads us to the questions. Do the lodgepole, does Tamias speciosus and alpinus, do they differ in their response to novelty? In particular, does our less stressed out lodgepole chipmunk, is it more bold, is it more active, is it more exploratory than our alpine chipmunk? So to do that with the chipmunks that we caught, once we had an individual we had marked and that we had identified, if we ever caught it again, we could then be like, cool, we can stick it in the arena and film it. And so we use these things called open field tests, which are standard tests of behavior across animals to measure things like boldness, exploration, anxiety, stress response, and things like that. And basically, the arena just provides a neutral space that every individual is subjected to, and then you can put it in for a standardized period of time, measure its behavioral response, and look for differences between individuals. So I'm going to hop out, and I have a video ready for y'all to see what this looks like. And so I think in the arena right now is an alpine chipmunk, alpinus. And that's basically what they spend most of the first 2 minutes doing is jumping and looking for ways out, which, you know, good. That's what you want to see. You want to see, but then what often happens that kind of varies is how long they keep that up. So you'll have some individuals who'll spend their whole time high jumping, trying to get out there. You'll have other individuals who'll sniff around for like 15 seconds and then find a nice little corner and just decide like, oh, I live here now. And so you see the whole spectrum of behaviors in this arena. So there's a wide range of variation in how individuals respond to this test. And so our job then is to take those responses and see if they vary across individuals and to see if there's patterns across species. Let's see. Cool. So once we have the video, we can then take those videos into our video scoring software, Boris, and analyze them particular behaviors. We have a defined ethogram or a list of defined behaviors that we use to score the videos. And so first, our measure of boldness. So again, boldness being willingness to interact with a novel or potentially risky stimulus. And so for that, we use how long it takes an individual to enter the arena. So when an individual is tested in these arena tests, it's placed in a little holding area to the side, and the doors open. It's allowed to enter the arena at its own volition. So the time it takes to do that varies a lot, and it can maybe tell us something about how willing they are to kind of like rush headfirst into a potentially risky environment. For exploration, or their willingness to kind of explore, engage with unfamiliar environments, we use proportion of time spent on the edge of the arena versus the center. The edge of the arena kind of acts as a sort of place of safety, right? You kind of see that in a lot of animals, that like having a wall next to you kind of makes you feel a bit more safe and a little less risky. And so they're measuring how long they're spending along that wall versus up here in the open, where, I don't know, a hawk or a rogue biologist may come and snatch them up. Tells you a little bit about their penchant for risk. And then we also wanted to measure just overall activity, because again, we want to see how active those are, because just regular activity also is related to stress physiology. And we also wanted to kind of make sure we could tell the difference between exploration and just generally being more active. Like if you have an individual who's very hyper, but not necessarily very risk prone. And so again, go back to our questions. Given the behaviors and the measures that we developed, we've again asked them, is speciosus more bold than alpinus? And so we predict then that speciosus will enter the arena sooner than alpinus. In terms of activity, we'll predict that speciosus will spend more time moving, more time in locomotion than alpinus. And then for exploration, we predict that speciosus will spend less time on the edge of the arena than alpinus. So more time in the center, more time in the risky zone. So first, boldness, that latency to enter the arena. And so what we see in our data, and to analyze this, we use a Cox proportional hazard model, which is a form regression where we basically measure the time it takes for an individual to enter as kind of a dependent state event, and then cut it off at 60 seconds because in our experiment, we gave them 60 seconds to enter the arena, and then we kind of nudge them in. And so individuals who enter before 60 seconds kind of get plotted on this, like, we call it a survival curve, even though we're not technically measuring survival. And then we could see if there's a significant difference between the time it takes for the majority of individuals to enter the arena versus between species. What we see is that there's a trend that the lodgepoles tend to enter the arena a little faster than the alpines, but that difference does not seem to be particularly statistically significant. And we see that range of variation maybe isn't big enough between those two to really suss out if that pattern is robust. However, when we look at the proportion of time spent active, so time spent moving in the arena, we do see a really big difference in that the lodgepoles spend a lot more time moving than the alpines. Again, overall amount of time, they're not spending the majority of their time moving, again, because it's a 10-minute video. They get pretty wind beat after a while, and they just kind of decide, they're like, okay, I'm just gonna chill and see what happens. But even then, you can kind of see, even with these small numbers, you see that the alpines are almost most of their spending their motivation or their movement time around 0. All the lodgepoles are spending much more of their time moving. And then in exploration, we also see a pretty big difference in that lodgepoles are spending much more of their time in the center of that arena than the alpine chipmunks in that riskier zone. And so to respond to our questions, is Tamus speciosus more bold than alpinus? Not really, but they are more active and they are more threatening. So our take-home points for this point is that lodgepole chipmunks species tend to be more exploratory and more active than alpinus. However, boldness and exploration are not necessarily correlated, which we'll talk about in a second. And it leads us in this kind of tracks with our hypothesis that our more generalist or more climate resilient species seems to be exhibiting these more novelty prone behaviors. It seems to be less reactive to stress and better easy to cope with the unfamiliar. And so interesting, cool. We have a difference between species. What does that mean? So now we're getting to our last section, which is kind of a coda to our discussion of behavior, moving into the realm of personality and repeatability. So personality and repeatability are an important question in the field of behavior because it really answers that fundamental question of how does natural selection act on behavioral traits, right? So we all kind of intuitively can sort of see what a behavior is, right? But like, how does selection do a behavior? And so what a lot of behavioral biologists have kind of settled on is that like all traits, it needs to be heritable. And for something to be heritable and be consistent, it needs to be what we call repeatable. And so that trait within a degree of variation occurs consistently in context for a given individual to be a trait that can be acted upon by selection. And so this consistent pattern of behavior across behavioral traits is referred to as an animal's personality. And so, anyway, doesn't matter. So to measure repeatability, it's kind of a pretty simple way. If you're used to the phenotypic plasticity literature, thinking about the plasticity or lability of traits, you have what we call here a reaction norm. And so, for example, you have two individuals, individual 1, individual 2, and you have the same behavior being measured at event 1 and event 2. And so for this behavior, you see like a fairly flat line. So you'd say this behavior has a pretty high degree of repeatability, while in this, for individual 2, there's a much steeper difference between the behavior at event 1 and event 2. And so you say that individual would have a lower repeatability. Another way of thinking about personality is a concept we call behavioral syndromes, which is something that I mentioned earlier. And so behavioral syndromes are basically behaviors that co-vary and co-occur in similar contexts and environments. And I mentioned that boldness and exploration, they're both behaviors dealing with novelty and stress and risk, tend to be grouped together as behavioral syndrome. And so if we're going to measure something as a behavioral syndrome, we can also sort of take a similar sort of correlative reaction norm approach, right? Where instead of two different individuals, we have two different behaviors. We have behavior 1, behavior 2. We have event 1 and event 2. And while these behaviors don't necessarily have the same exact value or anything, they both vary along the same slope, right? So even though they're not necessarily consistent between event 1 and event 2, because the slope of relationship is the same. We can start to say there's evidence of these two behaviors co-varying and forming a syndrome. And so with my behavior data that I had and was really proud of, I decided I really wanted to sort of start to pick apart this question of repeatability and the syndrome question. And so, are our measures of boldness and exploration behavior repeatable? And do our measures of boldness and exploration co-vary in our two species? So those were the two main questions that drove this last section of the dissertation. And here are the results. Yeah, behavior's messy, you know. And so what we see is, first of all, for boldness, we don't see very much repeatability at all. So we have an R, so the R of correlation of about 0.109, and of course non-significant. Exploration shows a bit higher level of repeatability, and when you look at reviews of behavior and repeatability in the literature, that number about R equal 0.3 is about average you see in a lot of repeatability studies. And so, which was promising, but we, to assess for statistical significance, we did a bootstrap permutation test, which did not reveal significance for that. And so my hunch is that it's a sample size issue. And I think if we were to put more in, then maybe we could see something, but maybe not. And then also our data showed that there wasn't really much of a correlation between boldness and exploration, at least in the ways that we measured it. And so are boldness and exploration behavior repeatable? Nah. And are they covariant? Nah. But so that really raises some important questions then about the behaviors that we measure, because these behaviors aren't repeatable, but that species difference, especially in exploration and activity, is pretty robust. So what is that telling us? I don't know. And so again, I think sample size plays a significant role. And I think one of the other things that, you know, again, the PhD, it's a lot of study in hindsight, right? Where I think how we measure or how we define a repeated measure, I think can have a really big influence on what counts as repeatability. So does repeating a measure of an individual's boldness behavior within the same season, is that indicative of a repeated personality trait versus going from year to year and repeating that behavioral measure? And so I think there's a lot of debate in that in the literature. Chipmunks may not be the best system to do that, since they live about, on average, 3 years in the wild, and usually less. So, but with more data and more time, I think we could potentially really build that up a bit more. Oh, I'm out of time. And so the observed differences in behavior might be just emerging from underlying non-behavioral processes as well. And so final thoughts. Not much evidence that intrinsic demographic variation is driving population range shifts. Species differ in behavior, but these differences are not necessarily repeatable. And individual differences may yet be driving climate responses, and we can't discount extrinsic and stochastic factors and their predominance in what's driving these population range shifts. So, what next? So these are kind of the questions that still kind of occupy my brain regarding the chipmunks. Will I come back to them? Maybe. I want to, but the important thing is I don't have to. So yeah, important distinction. But if anyone wants to learn more about the chipmunks and wants to go out with me one summer and maybe test some of these, I would very much be down after. But first I have to make time for my actual job, which is where I'm at now. I'm now an NSF postdoctoral fellow up in Canada at University of British Columbia, supervised by fellow Berkeley alum, Caitlin Gaynor. And our project's looking at sort of the role of individual behavior and habitat preference in driving climate-induced range shifts in mammals. I know, very original, very different from what I'm doing right now. But basically hoping to expand the scope of taxa and expand the scope on the geographic landscape and to look at larger patterns of range shift, and then also moving from rodents to carnivores and starting a camera trap project to look at space use and habitat preference in bobcats and how that might be driving dynamics at their northern range front, which is kind of along the southern border of Canada. All right, that is the science, and I'm over time, so feel free to leave if you've got to. But I've got all the sappy acknowledgments I want to get through, so you're gonna want to stay for that. This is good. But yeah, so first of all, I want to thank Eileen. Especially for that wonderful introduction she gave me, but in particular for just being an amazing, supportive, intelligent, and responsive and kind mentor, and really, man, my time at Berkeley would have been very different if Eileen were not my mentor, and I really appreciate her for that. This was the one picture I could find of us together, or just the two of us. But of course it's us with our back turns. This is at Chimney Rock, if anyone can recognize. This is the last running of behavioral ecology back in spring 2019, where we took the students out to watch elephant seals from the point. And so, of course, Eileen and I, rather than pontificating about the finer nuances of behavioral theory, are also just staring at elephant seals as well. This is also from behavioral ecology, and this is, and I think these images kind of sum up sort of what I take away from kind of Eileen being a mentor, and just a love, respect, and just fascination with the animals that we share the world with. I think that approach to doing research, appreciating animals as their whole selves in their natural environments, in their natural contexts, and just diving deep into the little details that make them tick. That's something I'll always carry with me, and something I've always loved about science and the work that we do, and I think something that resonated with me when I joined the lab. And then also just the importance on sharing with the world what we do and prioritizing that on an equal footing with all the other work that we do, in the form of, whether it be the form of teaching or outreach, or just, I don't know, nerding out about animals on a nature hike with your captive friends, with me, you too. And so I feel like this really encapsulates how I feel about my time. So I appreciate that. And also, can't forget. I had to do one. And on top of Eileen, and just not Eileen just as a person, but also in the lab that Eileen cultivated, and all of my lab mates over the years. I mentioned a little bit in the beginning, but I want to say it again, that you guys have formed such a solid community for me in my time here. Like, having folks that I can always rely on, even though we're not necessarily working on the same things, I know I can always go to you if I ever need help, or just like to vent about anything. I know y'all have been there for me, and that's been really, it's been really important as I've made it through this PhD journey. And yeah, just shout out to the Lacey Lab that are here. I think Shannon might be on Zoom, and if you are, what's up, Shannon? And yeah, all right, I'm moving on. I can't get sappy. I always gotta shout out the time I spent teaching and mentoring. That part of my PhD really kind of carried me through, definitely in the parts where the science wasn't really working out in ways, and you started to hit that like mid PhD slump, and you're just kind of like, okay, I have data, what the hell do I do with it? Like, you can always kind of like rely on being able to teach, especially classes like IB 104 with Jim and Rory and Alan, or teaching behavior and behavioral ecology with Eileen, or field courses like that, where you can really kind of get out there and share the love you have for nature with the students, maybe inspire a few others to share that love. Not necessarily out there to create other biologists. I mean, if they decide to become biologists, that's cool too. But I really think being out there and learning about the world around you in a deep way makes you just a better human being overall, makes you more connected, makes you more grounded, gives you something beyond yourself to believe in. And so I really want to carry that forward with me as I go. Gotta shout out the IB graduate students. I couldn't fit all of them on there, obviously. But man, this is the coolest cohort of graduate students I've ever met. And like, people say a lot of things about their grad career, but I feel like overall, for all the people I've talked to who've gone to grad school and other places, I don't think any of them have a grad cohort that's as tight and as bonded as we are. Whether it be on the picket line, going on trips, whether it be us as GSIs eating Puerto Rican food on the roof of Dan's Subaru, or you know, or when we send each other off in style after we finish, or when we get one of us gets married, or when we decide to eschew our scientific duties to make music. The grads here have been real solid, and yeah, I look forward to seeing what everyone the future holds for all of us, and y'all better come visit me in Canada. I also got to shout out some of course, the non-grad school friends, all of the people who I've known for years, who have like kind of held me down, and also people I've met since I've come here who aren't Berkeley folks, who also keep me grounded. And remind me, you know, that life is a big, beautiful, complicated thing, and while grad school and science is a large part of it, it is not the only thing. My family, I would definitely not be here at all without them. Both of my parents are educators, and so education and hard work and curiosity and knowledge are always kind of baked into our DNA growing. And so they always expected the best of us and to give our best and to do everything to the fullest of our abilities. And you know, I haven't always met that expectation, but but it is a goal I've always tried to set for myself. My sister as well, my sister's a few years older than me, and she has always been kind of like my model of like how to like do things correctly. Like every time I'm kind of struggling, trying to figure out how to do things, I always kind of ask like, well, man, what would Kaylee do? What would my sister do? How to get through this. And so I've always looked to her as an inspiration in that regard. And then she also, we were also very lucky about halfway through my PhD in 2020, or in 2019, at the very end of 2019, that we had a new member join the family, my nephew, Josiah. That's him as a little newborn right there. And then that's older Joe there. Maybe you can see the resemblance between that and that handsome toddler there. Mostly in the forehead. But he's been a real light inspiration to me as I've been finishing the last couple of years of the PhD, getting to that last slug. He came out to visit when I walked in May, and he got to see California, and took him up to like the Botanical Gardens, and he's just kind of like running around having a great time. And so my family is the reason I do what I do, and what I do is to make them proud and to honor the hard work they've done. Last but not least, I gotta thank Tara Harmon. She's gonna hate every second of this, but it's my finishing talk, so too bad. Tara, you are my absolute favorite person, and I could not have made it these last few years without your support and your friendship and your kindness. And whether it be just all of your support and kind of helping me get through the later stages of writing, giving me a place to live for 2 weeks after I got kicked out of my apartment, and just overall being an absolute solid person. And then also just being my adventure buddy and my dance partner and my fellow in exploring nature and my way to learn about the complex fire regimes of California. Anyway, I'll be there. That's all. So that's it. We're done. We're a bit over time. Apologies. And to quote another Nipsey Hussle album, the marathon continues. The work's not over. Science will happen. Life happens. And I appreciate you all for coming.